So hi, everyone. My name is Alex, and I'm an Apache Cassandra committer. I'm pleased to be here in Colombia and in Medellin, and it's an extremely big honor for me to be a part of this event. Today, we're going to talk about the on-disk storage. And the title of the talk was inspired by Álvaro Videla, who's going to be the next speaker. This is my first time I'm actually presenting before him. I wanted to say extra thanks for inspiration. And his talk was called What We Talk About When We Talk About Distributed Systems. And I thought that there is a need to create an overview or introduction for disk-related and I/O subjects. So let's talk about the reasons about why I wanted to give this talk. The amounts of data processed by applications are constantly growing. With this growth, scaling storage becomes more and more challenging. Since database systems, like every one of them, has their own trade-off, and understanding them becomes more and more crucial, because it helps us to pick the right one from so many available choices. This talk aims to summarize the practices since the latest developments open up lots of new opportunities, and try to build the vocabulary and gain the intuition to point to the worthy sources. Because finding the information on this subject is, to be honest, not a trivial matter, so I had to go through several books, many blog posts, and lots of other materials to kind of summarize it for you. So I've tried to also put together a series of blog posts that you will be able to OK. So you will be able to access it by the link that I'm going to be giving in the end of the presentation. And this is definitely not a simple subject, but I will try my best to make this talk free of snake oil, silver bullets, and present pure facts, and hopefully no biases or speculations. Before we dig into the storage system themselves, let's start with some terminology. One of the most important things to think about when you are picking a storage system is an access pattern, since it's going to put some caps on the abilities and the performance of the storage system that you're building. Usually, we distinguish between the random I/O and the sequential I/O patterns. By sequential access, we usually mean reading contiguous memory segments monotonically going from the lower offsets to the higher ones. And random access is different in that it doesn't read the contiguous memory segments, and it just jumps from one place to another. So it's random because the seeks are hard to predict, and they may span many pages. The sequential writes imply that we're going to write file blocks without issuing any seeks in between. And for CPU and operating system, sequential usually means predictable, which means less page cache misses and lots of prefetching can be done, so operating system can do certain optimizations. It is important to remember that the sequential writes do not always result into the sequential reads. Data that was written closely will not necessarily be read together. Sequential reads are mostly used when reading large continuous blobs of data, and for instance, like logs or range scans. Let's think for a minute how we can achieve the sequential access. In order to be able to write your data sequentially, you often have to buffer it. And pre-sorting the data will help to prepare the data to be laid out for the sequential reads later. Random writes are bad for both the SSDs and hard disk drives, but for different reasons. On hard disk drives, random I/O is bad because the ARM has to seek for a correct track and move from one position to another. SSDs, on contrary, have a problem with unaligned and random writes because they have a process which is called write amplification. The flash translation layer, a subsystem which is responsible for managing SSD blocks, eventually runs out of empty pages after doing lots of writes. And because SSDs are based on the NAND storage and AND, and in order to move blocks, they first have to be nullified, so completely erased. An expensive garbage collection process has to relocate empty blocks and erase them before being able to write actual pages. Sometimes random and sequential I/O are actually intersecting, so you often see the patterns used together. And for instance, B-trees do lots of random seeks in order to locate the interior nodes, but whenever they reach the leaf level, they usually do the sequential read. More on that in a couple of slides. Another important concept is mutability or immutability of the data structure. This is also has significant implication for the disk layout and general process of data structure construction and maintenance. Mutable data structures usually pre-allocate memory in order to allow in-place updates. This usually results into lots of random I/O, especially during writes. More on that a little bit later. Since updates are made in place, there will be no shadowing. To be precise, like reading from multiple sources and then resolving the conflicts when reading from these multiple sources. So none of this is going to be required. Concurrent accesses and modification have to be guarded by the structures such as locks and latches, which is also rather complicated. On contrary, immutable data structures require in-memory buffering, but for that they can guarantee the writes to be sequential. Because of the immutability and the fact that the files are not modified on the disk, the immutable data structures usually require reading from multiple sources and, well, reconciling the data, well, on contrary to the mutable ones. Now, as the basic web vocabulary is covered, let's talk about the log-structured merge trees. LSM trees is an immutable data structure. It's disk resident, and it's optimized for disk writes. But it also can maintain the reasonably acceptable read performance. So even though it's optimized for writes, it is still OK for reads. LSM trees have been getting more attention because they can eliminate random I/O during insert, update, or delete operations. So there are no disk seeks required for inserts, updates, and deletes. And to give you some context, things like log-structured merge trees are widely used in databases, for instance, RockDBs or Apache Cassandra. In order to allow sequential writes, LSM trees batch up writes and updates in the memory resident table. It is often implemented as a data structure which allows logarithmic lookups, such as binary search tree or a skip list, something like that. When its size reaches a certain threshold, it's being written on disk. This operation is called flush. Retrieving the data, or reading it, requires searching all the disk resident parts of the tree and the in-memory table as well, and then merging their contents together before returning the result to the end user. Disk resident table files are immutable. They've been written on the disk once and cannot be modified afterwards. They can only be deleted on the later stage. As you can see, LSM storage converts, quote unquote, random writes into sequential by means of buffering. So we buffer things in the memory table, then flush it, and then the process continues. Many modern LSM tree implementations, such as, for instance, Apache Cassandra or RocksDB that I just mentioned, choose the sorted string tables as a file format. They choose it mostly because of its simplicity, because it's easy to implement, and reads, writes, and searches are quite simple inside of the implementation. The SS tables are persistent, immutable maps from keys to values, which means that they are stored on the disk, and they're always ordered by the key. Therefore, it's called sorted string tables. Every table value in SS table usually has a timestamp associated with this. It specifies the write time for inserts and updates, which are, to be honest, often indistinguishable, and the removal time for the deletes. Structurally, SS tables are split in two parts, the index block and the data block. The index block contains keys mapped to the data block offsets in order to be able to locate it and then follow the pointer and then read the data. Index is often implemented using a format optimized for quick searches such as Btree or a point query optimized one such as, for instance, hash table. Data block consists of sequentially written key-value pairs, each one appearing just once. Because, well, sorted things, you cannot really have, well, repeated keys. That would be rather unreasonable. SS tables have several very nice properties. For instance, point queries, which means finding value by the key, can be done quickly by searching index block and locating the data by following the offset. Sequential scans, which means iterating over all key-value pairs in a specific key range, can be done efficiently by finding the item in the index, following the offset, and then sequentially reading the records one after another from the data block. Logically, SS tables represent a snapshot of the database operations over the period in time. Or you may think of it as a log, even. An SS table is created with the flush process, as we just seen on the previous slide, from memory resident table that was serving as a buffer for the operations against the database for the certain period. So this is why I say that this is a kind of a snapshot or a log. Because SS tables are immutable, they're written sequentially and hold no empty space for modifications. So inserts, updates, or delete operations would, as it seems, require rewriting an entire file in order to update just one record. Of course, that would be completely unreasonable to do. So all operations, as we discussed, are buffered in the memory resident table. Over the time, the amount of the tables that get flushed will grow, which will make reads more and more expensive. Data for the same key might end up in the multiple files holding versions of the same record, or redundant records which got shadowed by the later deletes. Because the files are immutable, we don't delete them, so there will be duplicates. In order to reduce cost of reads, reconcile space occupied by the shadowed objects, reduce the amount of disk resident tables, LSM trees require a process that reads complete SS tables from the disk and merges them together. This process is called compaction. As we discussed, SS tables are sorted by the key, and compaction works like merge sort. This operation is quite efficient. The records are read from several sources sequentially, and merged output can be written to the file right away, also sequentially. One of the advantages of the merge sort is that it can work efficiently even when merging large files that don't fit in memory. Resulting, a table preserves the order of the original SS tables. Just merge one. During this process, merged SS tables are discarded and are replaced with their compacted version. After compaction is done, the amount of SS tables that have to be addressed is reduced, which all makes the queries more efficient. So we had, for instance, like 5 or 4 SS tables. We merged them together. We just got one of them or one resulting SS table that we will need to address. So from the data standpoint, merge is reconciling the records from the multiple sources. Records usually have a key and a timestamp associated with them. For example, if one of the SS table records has a later timestamp or larger one, previous can be discarded. In order to support deletes, something which is called dormant certificates or tombstones is used. So these dormant certificates or tombstones indicate that the record with a certain key was removed from the database. During the merge process, records shadowed by the tombstones are ignored and are not written to the resulted merge table. In the same way, they are not returned to the end user when the query is done against the database. Considering a more specific example, here, a record with the key Alex has a written timestamp 100 at first. And on the later stage, it was updated with the timestamp of 200 and a new phone number. Resulting table will use an updated value for the key because the timestamp is larger. The record with the key John gets deleted in the later SS table and gets discarded during the merge process and does not show up in the merged SS table. The other two entries are taken as is because they were not shadowed, so there was no overlap for these keys in these two tables. Let's summarize what we just learned about the LSM trees. First and foremost, they are immutable. The SS tables are written on disk once and are never updated. To reconcile the space occupied by removed items and merge the same key data from the multiple files, SS tables are merged and discarded during the compaction process. They are optimized for writes. So writes are buffered and flushed on the disk sequentially, potentially allowing good spatial locality on the disk. Reads might require accessing data from multiple sources, since the data for the same key may be written several times or at different times to several different tables, and might be, well, kind of far away from each other. Records have to go through the merge process before they can be returned to the client. And the whole LSM concept requires maintenance, which is called compaction. The heavy workloads can saturate I/O by just reads and flushes, therefore stalling the compaction process. So that would mean that the compaction would be lagging, which would be slowing the reads, increasing the CPU and I/O pressure, and making the matters worse. So this could be kind of a spiral of death for the LSM tree-like storage. So Btree is a popular indexing data structure, which is kind of, I'm trying to contrast with the LSM tree. It is coming in many variations and used in many databases, for instance, MySQL, InnoDB, or PostgreSQL, and even several file systems. One of the most prominent papers on B-trees is called Ubiquitous B-trees, which describes in a great detail several possible variants of B-trees and their applications. Binary trees are binary trees is kind of a grandparent or parent of the B-trees, are an in-memory data structure, and because of the balancing, which is a need to keep the depth of all the subtrees to the minimum, and the low fan-out, which means that binary tree has only 2 child nodes, so each node of the binary tree has only 2 children. Because of these 2 factors, the binary trees will not work well on the disk. This is why they were kind of evolved into the B-trees. B-trees allow storing more than 2 pointers per node and work very well with block devices by matching the node size to the page size, which is usually a multiple of 4K. And some implementations today use larger node sizes, but they always operate with the multiples of the 4K. The B-trees have following properties. Well, first of all, they're sorted, which allows sequential access and sequential scans and simplifies the lookups. They are self-balancing, so there is, well, no need to balance the tree during insertion and deletion. And when the B-tree is full, it is B-tree node is full, it is split in 2. And when the occupancy of 2 neighboring nodes is reaching a certain threshold, they can be even merged together. This also means that leaves are always equally distant from the root and require the same amount of steps in order to perform a lookup operation. The B-trees also guarantee the logarithmic lookup time, which makes them a good choice for database indexes where lookup times are important. And it's also very important to contrast them to LSM trees in the way they are mutable. So inserts, updates, and deletes, also subsequent splits and merges, are performed on disk in place. In order to make the in-place updates possible, a certain amount of reserved space overhead is required. So empty space, which is not used currently by the B-tree, has still to be reserved in order to facilitate further or future splits and merges, updates, deletes, removals, and so forth. B-tree can be organized as a clustered index where the actual data is stored on the leaf nodes, or for instance, as a heap file where the index and the data files are split. Let's first take a closer look at the Btree building blocks. The Btrees have several node types. They have root, internal, and leaf nodes. The root has no so-called parents, which means that it is not a child for any other node. Internal nodes are ones that have both parent and the children. They're kind of connecting the root node with the leaf nodes. Leaf nodes carry the data and have no children. Btrees are characterized by three things. First of all, branching factor, the amount of pointers to the child nodes. So the occupancy is the second important characteristic of the Btrees, is how many pointers the child items to the child items the node is currently holding out of maximum available. For example, if the tree branching factor is n, and the node currently is holding n divided by 2 pointers, its occupancy is 50%. The third characteristic is called height, and it means that how many levels there are between like the top and the bottom. So on this image, you can see the tree of 3 levels. Every non-leaf node in the tree holds keys, which are index entries, and the pointers to the subtrees. The leaf nodes may also hold a pointer to the previous and the next nodes on the same level, forming a doubly linked list of sibling nodes on the very bottom. And all keys in the nodes are usually sorted. As you have seen on the previous slide, nodes consist of the sorted keys and pointers. And first and the last pointers are kind of special cases. They're pointing to the subtrees in which all the entries are greater than or equal the first key, or the leftmost child, or greater than the last key in the case of the rightmost child. All the other pointers point to the subtree that holds the keys greater than predecessor key and less than or equal than the successor key. When performing the lookups, search starts on the root node and follows internal nodes recursively down to the leaf level. On each level, search field is reduced to the child subtree by following the child pointer. Range of this child subtree includes the searched value. However, we cannot know that the value is going to be there until we reach the leaf nodes. When the point query is performed, search is complete after locating the leaf node. In case of the range scan, keys and values in the find leaf and the sibling leaves are traversed until the end of the range is reached. You can think of it as a point queries going vertically, and the range scans go in first vertically and then continue in horizontally. This is also kind of a flashback to what we've been talking about when we have a random I/O in order to locate the node, the leaf, and then sequential scan in order to read the range. In terms of complexity, Btrees guarantee a logarithmic lookup because finding a key with the node is performed using the binary search. When performing insertions, we first have to locate the leaf, the target leaf. For that, we can use the algorithm that we just discussed on the previous slide. After the target leaf is located and the key and values are appended to it, the key and value have to be appended to it. If the leaf doesn't have enough free space, the situation is called overflow, and the leaf has to be split in 2 parts. This is done by allocating a new leaf, moving half of the elements to it, and appending the newly allocated leaf's key and its pointer to the parent. If the parent doesn't have the free space either, the split is performed on the parent level as well, and operation continues recursively until the root is reached. When root overflows, its contents are split between newly allocated nodes and the root node itself is overridden to avoid relocation. This is usually done for the simplicity of the on-disk implementation. This also implies that the tree and its height is always growing from the root down, or up, whatever the way you can imagine it. This process helps to keep the tree balanced because the height is always same across the whole tree. Deletions are similar to insertions, but may cause the node merge, so not the split, but merge, which is an operation reverse to split when target becomes so-called deficient. Amount of splits and merges depends on the branching factor and usually should be minimized in order to reduce the amount of I/O operations. So in order to summarize the information that we just looked over for the B-trees, first of all, they are mutable, and they allow for in-place updates by introducing some space overhead and kind of more involved write path. Second of all, they are read-optimized, so they do not require reading from and subsequently merging data from multiple sources like LSM trees did, which simplifies the read path significantly. Writes and deletes might trigger a cascade of node splits and merges, which makes certain amount of write operations more expensive. And there are some techniques that implementers are using to kind of amortize the costs by, for instance, batching updates, pre-allocating nodes, keeping the node occupancy low, transferring the data from the more full nodes to the less full nodes, et cetera, et cetera, et cetera. They are optimized for the paged environments, meaning like block storage, where byte addressing is not possible. So maybe things are going to change with the NVM storage. And mutable implementation needs some overhead to allow in-place updates and inserts. Fragmentation caused by the frequent updates might make additional or add more maintenance and block rewrites. However, usually B-trees usually require less maintenance than the LSM trees. The concurrent accesses and reader-writer isolation involves chains of locks and latches, which makes the implementation slightly more complex. We'll try to summarize all that we just learned about these two contrasting data structures in the following several slides. When developing a storage system, we are always confronted with the same challenges and have to consider, well, rather same factors. Making a decision about what to optimize for has a substantial influence on the end result. One can spend more time during the write in order to lay down the data structure which will be more efficient for reads. You can reserve extra space for in-place updates and facilitate faster writes. You can buffer the data in memory in order to ensure sequential write operations. However, you cannot do all of it at once. An ideal storage system will have the lowest read cost, lowest write cost, have no overhead, and in practice, of course, we always have to find a compromise between multiple factors. And it's important to understand these compromises. The researchers from the Harvard DB lab summarized these three key parameters and formulated it as if we had three kind of points we could optimize for: reads, updates, and memory overheads. Understanding which of these parameters are more important for your use case influences the choice of the data structures, accesses, methods, and even suitability for certain workloads, as the algorithms are tailored, always tailored, having specific use case in mind. The RAM conjecture states that setting an upper bound for the two of the mentioned overheads also sets a lower bound for the third one. For example, B-trees are read-optimized and have less write overhead, but have to reserve empty space for the updates. LSM trees have less space overhead at the cost of read overhead brought by having to access multiple disk-resident tables during the read. These three parameters form a competing triangle, and improvement on one side will imply the compromise on the other. Btree is optimized for the read performance. Index is laid out in the way that is minimizing the disk access on the disk accesses, and requirements of tree traversals. Only a single file disk access has to be accessed in order to locate the data. And on contrary, LSM trees are optimized for write performance. Both updates and deletes do not require locating the nodes on disk and guarantee the sequential writes by buffering all insert updates and delete operation in the memory resident tables. So you have seen that there are data structures optimized for each desired property. Using the adaptive data structures allows for better read performance at the price of higher maintenance cost. Adding the metadata facilitating traversals, like for instance fractional cascading, will have an impact on write time and take space, but will improve the read time. Optimizing for memory efficiency using compression will add some overhead for packing and unpacking the data structures, but will improve the memory overhead. Sometimes you can even trade functionality for efficiency. For example, heap files and hash indexes have great performance guarantees and smaller space overhead during the file format simplicity at the price of not being able to perform anything but the point query. You can also trade precision for efficiency by using approximate data structures such as Bloom filter, hyperlog, count-min sketch, and many others. So these three tunables, read, update, and memory overheads, can help you to evaluate your database and deeper understand the workloads it's best suitable for. All of them are quite intuitive, and it's often easy to sort the storage into one of the three buckets and guess how it's going to perform, then validate your hypothesis by extensive testing. Of course, there are other important factors to consider when evaluating a storage system, such as maintenance overhead, operational simplicity, system requirements, suitability for frequent updates, deletes, access patterns, and so on and so forth. RAM conjecture is just the kind of a rule of thumb that helps to develop an intuition and give you a first direction. Understanding your workload is the first step to build a scalable backend. Many things may vary from implementation to implementation, and even two databases that use the similar storage design principle may end up performing differently. Databases are complex systems which have many moving parts and are an important part of the applications that we're building. I hope this information will help you to peek under the hood of the databases, and knowing the difference between the underlying data structures and their inner doings, decide what is best for you. If you're curious and interested in the subject, I highly recommend read several more books, and these are kind of the most prominent or ones that I found most useful while preparing for this talk. Other than that, I have created a series of 5 blog posts, which would result in probably 1.5 hours of active reading, with many other links explaining all the concepts also explained here in even more details. If you follow the bit.ly scaleconf.co link, you will find it. And also, if you like, you can follow me on Twitter. I'm currently working on the new series, which is going to explain the distributed system concepts and consensus in more details. And I would like to thank you all for letting me share this all with you. This is an awesome crowd. This is an awesome conference. Thank you very much. Have a very nice day. Thank you.